Okay, let's unpack this. I mean, think about building something really complex, like a game engine. All those different bits, physics, rendering, AI, UI, how do they talk to each other without turning into spaghetti code?
Right. And then, debugging.
Yeah,
When something breaks deep inside, how do you even figure out the sequence of events? It's a huge challenge.
exactly. Dependencies, hidden bugs, nightmare stuff. But we have this document here, kind of a blueprint for a mini educational game engine. It outlines some interesting solutions.
Yeah, it lays out systems designed to tackle exactly those problems.
Mm-hmm.
We're looking at how it handles communication between different parts and also how it implements some really detailed low-level function tracing.
So our mission for this deep dive is to really get into this document. We want to understand these systems, figure out how they work, especially the angle of targeting the web with WebAssembly.
Yep. We'll look at an event and delegate system first. That's for the communication part. Then we'll dive into this pretty clever AOP-like logging system. Uses a sort of mini header tool, kind of like Unreal's UHT,
AOP, aspect-oriented programming.
Sort of, yeah. A way to inject logging without cluttering the main code. And crucially, how all this logging output actually surfaces when you run it in a browser using WASM.
Okay, sounds good. Let's start with the events and delegates. What's the core problem this system is trying to fix in the engine's design?
It really boils down to coupling.
Yeah.
Tight coupling. You absolutely want to avoid a situation where, say, your player object, every time it takes damage, needs to know specifically about the UI system to call update health bar and the audio system to call play heard sound and maybe even a logging system directly.
Right, because then the player depends directly on all those other systems. Add a new system that cares about damage. You have to change the player code. That gets messy fast.
Exactly. It makes changes hard, reuse difficult.
Yeah.
The event delegate pattern flips that. Instead of the player making direct calls, it just announces, hey, I took damage. It broadcasts an event.
Then anyone interested just listens.
Precisely. The UI, the audio, anyone they can subscribe to, that damage-taken event. The player has no idea who's listening or even if anyone is listening. It just sends out the signal.
Okay, so the document mentions some key terms. Delegate, single-cast, multi-cast, event. Let's break those down.
Okay, so a delegate, at its core, is like a type-safe function pointer. It knows the signature, what arguments a function takes, what it returns, but it doesn't necessarily point to a specific function. Yet, it's a placeholder.
Like a contract for a function call. I need this kind of function.
Yeah, that's a good way to put it. Now, a single-cast delegate can only hold on to one of those function references at a time. Useful, but limited for events.
Because events often need multiple reactions.
Exactly. Which brings us to the multicast delegate. That's the key here. You can hold a whole list of function references. When you broadcast on a multicast delegate, it just goes through its list and calls every single subscribed function.
And the event itself is often just that multicast delegate owned by the object that might trigger it.
That's a very common way to implement it, yeah. The object experiencing something, like the player, owns a multicast delegate called, say, undamaged. When damage happens, it calls broadcast on undamaged.
And it can pass data along too, right? Like the amount of damage?
Yep. The broadcast function can take arguments, and those get passed along to all the subscribed listeners, so the UI knows how much to update the health bar by.
Makes sense. The document also mentions DelegateHandle. What's that for?
Ah, right. When you subscribe a function to a multicast delegate, you usually get back a delegate handle. It's like a receipt, a unique ID for that specific subscription.
So you can unsubscribe later.
Exactly. You hold on to that handle, and when you don't need to listen anymore, you use the handle to tell the delegate, okay, remove this specific listener from your list. Keeps things clean.
And the delegate and multicast delegate templates are just the C++ mechanics behind it all?
Pretty much. They handle storing the listeners, making sure types match, calling them safely. The document's examples show objects owning their own delegates, like the player having undamaged, which is a really clean way to achieve that decoupling.
So the player's take damage function does its thing, updates health, then just calls ondamaged.broadcast damage amount.
Yep, fire and forget, essentially. Doesn't care who's listening.
And then the UI system, maybe in its setup code, does something like player ondamaged.add to hook up its update health bar function.
That's the pattern. Audio system does the same for its sound function. Maybe a statistics system adds a listener too. They all just register their interests.
The workflow diagram makes it clear. One trigger, one broadcast, many independent reactions. That decoupling is really powerful.
It really is. And notice, the logging system can just be another subscriber. It hooks into unplayer damaged and calls UELog in its handler.
Right, so you get these high-level logs of important game events happening, tied nicely to the architecture.
Okay, so that covers the big picture events. Player took damage, quest completed, things like that. But what if you need to debug something much, much deeper? Like you suspect a specific function is getting called with wrong values, or maybe not called at all.
Yeah, the event logs won't show you that level of detail. You need to see the function-by-function execution flow.
Exactly. And that's where this second system, the AOP-like logging using the mini header tool, comes into play. The goal here is detailed tracing, but crucially, without making developers manually write UELog calls everywhere.
Because that would be incredibly tedious and clutter the code.
Totally.
Yeah.
So this approach uses aspect-oriented programming ideas. The aspect is the logging behavior entering a function, exiting it, maybe logging parameters. We want to apply this aspect across many functions without mixing the logging code directly into the function's main logic.
And how does it know which functions to apply this logging aspect to?
That's where the metadata comes in. Developers mark functions in the header files. They use a special macro, like UFUNCTION, and add a tag inside it, like LogTrace.
Ah, so UFUNCTION LogTrace is the signal.
It's the signal to the build tooling. Specifically to this mini header tool, the document mentions a script like generateHeaders.py. This tool runs before the C++ compiler.
And it scans the headers for that LogTrace tag.
Exactly. It parses the headers, finds functions marked LogTrace. And here's the clever part. Instead of the developer writing the definition for that function directly,
The tool generates it.
yes, it generates the definition in a separate file, usually something like myclass.generated.cpp. This generated function acts as a wrapper.
Okay, a wrapper. What does it wrap?
It wraps the developer's actual logic. Inside this generated wrapper, the tool automatically inserts the UELog calls, typically a one at the very beginning saying entering function name and one just before it returns saying exiting function name.
And the developer's code, where does that live?
Between those generated log calls, the wrapper calls a different function, often named something like function name implementation. That function is what the developer actually writes in their normal .cpp file.
Uh-huh. So the developer writes the implementation version containing the core logic.
Right. And their original header declaration with UFUNCTION, LogTrace,
Yeah.
is clean, and their .cpp file with the implementation logic is also clean. No logging calls cluttering it up.
All that logging boilerplate gets pushed into the generated file by the tool.
Precisely. It separates the concern of logging from the concern of the function's actual job.
That header tool script must need quite a bit of information to generate the wrapper correctly, though.
Oh, absolutely. It needs to parse the UFUNCTION macro to find LogTrace. But critically, it needs the full function signature, return type, name, and crucially, the type and name of every single parameter.
The types, okay, that makes sense for generating the function definition, but why the parameter name?
For useful logging. When it generates that entering log message, you don't just want to know the function was called, you want to know the values it was called with, right?
Ah, of course. For debugging, seeing the input values is vital.
Exactly. So the generated UELog call needs to use the original parameter names to print their values. The UHT script needs those names to generate code like UELog. Value percent, message percent, value message. Getting that formatting right for all different parameter types is actually a non-trivial part of the UHT's job, as the document points out.
Let's walk through that example, myClass.myImportantFunction.
Okay, so in my class, the developer writes UFUNCTION, LogTrace, void myImportantFunction in value, fstring message,
Yeah?
and maybe declares a private void myImportantFunction implementation in value, string message.
Then in myClass.cpp, they write the actual logic inside the myImportantFunction implementation function body.
Correct. Now, the UHT script runs. It sees myImportantFunction in the header, sees LogTrace, it parses the signature. Then in myClass.generated.cpp, it generates the definition for the public myImportantFunction.
And that generated definition is the wrapper.
Yep. Conceptually, it looks something like this. CPP in myClass.generated.cpp, ulog, LogTrace, verbose, text entering myClass, myImportantFunction, value, percent message,
Yeah.
best generated log, ulog, LogTrace, verbose, text, entering, call the actual logic. Ulog, LogTrace, verbose, text, entering myImportantFunction implementation, value message, UELog, LogTrace, verbose, text exiting myClass, myImportantFunction, generated log, UELog, LogTrace, verbose, text exiting.
Wow. So the developer writes the clean interface and the clean implementation, and the tool stitches them together with the tracing logic automatically. That UHT workflow diagram makes perfect sense now. User writes AHA.cpp, tool reads, generates, generated.cpp, compiler builds everything.
That's the essence of it. AOP via code generation. Keeps the main code base clean, provides super detailed tracing when you need it.
But isn't there a risk of just oceans of log messages if you trace everything? Good question. Yeah, you need control. The document mentions 2 levels. First, compile time. The UHT script itself can be enabled or disabled, maybe with the command line flag like enable log tracing. If you build without that flag, no wrappers are generated, no tracing code is even compiled in.
Okay, so you can strip it out completely for, like, a release build.
Exactly. Then second, runtime control. The UE log system itself has categories and verbosity levels. The generated logs would likely use a specific category, maybe logtrace.
So you can filter them in runtime.
Yep. Using console commands or config files, you can set the verbosity for logtrace. Set it to warning or error, and you'll see none of the trace messages. Set it to verbose or log, and you'll see all the entering and exiting lines for the trace functions.
That offers good flexibility. Compile it in for debug builds, then turn the verbosity up or down as needed while testing.
It's a solid approach. So now we have these 2 logging mechanisms, high-level game events via the Delegate system and low-level function traces via the UHT system, both using UE log.
Right. Which brings us to the final piece. Where do you actually see all this output when you're targeting WebAssembly?
This is where things get really convenient, especially with toolchains like Mscripton, which the source mentions. Fundamentally, UILog ends up writing its output somewhere. In a typical C++ app, that's often std.count, the standard output stream.
The console window, basically.
Right. But when Mscripton compiles your C++ code to WebAssembly to run in a browser, it does something clever by default with std.count.
Where does it send it? Let me guess. The browser's developer console.
Bingo. Mscripton automatically redirects the WASM module's standard output and standard error streams directly into the JavaScript console you see in your browser's developer tools.
That's incredibly handy, seriously.
It really is. It means all the UE log output, whether it's from an event handler logging player damaged or from those detailed UHT-generated entering-exiting traces, it just appears right there in the browser console.
No extra setup. No WebSocket server to pipe logs to.
Nope. For standard Snapster redirection, it's just built-in Mscripton behavior. It makes debugging WASM module so much more straightforward because your C++ logs show up right alongside any JavaScript logs you might have.
So you run your engine build in the browser, pop open the dev console, F12 usually, and boom, there are your event logs, your function traces, everything. That's a huge win for web targets.
Absolutely. It drastically lowers the friction for debugging that kind of cross-compiled code.
Okay, let's pull this all together then. We've got the event delegate system for clean, high-level communication. Systems subscribe to things they care about, maybe log high-level events via UA log.
Right, great for architectural decoupling and understanding major game flow events.
Then we have the AOP-like tracing via the mini UHT, mark functions with LogTrace. The tool generates wrappers with detailed UE log calls for entry, exit, and parameters, keeping the user's code clean.
Giving you that deep, granular view of the actual code execution path when you need to hunt down tricky bugs.
And the key synergy, especially for web builds, is that both types of logs, the high-level event ones and the low-level trace ones, funnel through UE log, and thanks to Mscripton.
They all land directly in the browser's developer console. You get this layered debugging capability overview from events, deep dives from traces served up right where you need it for web development.
It really shows how combining thoughtful architecture like events, clever tooling like the UHT, and leveraging platform features like WASM's console output can make building and debugging complex software much more manageable.
Definitely. For you listening, understanding these kinds of patterns, decoupling with events, automating tracing with CodeGen, these are really valuable techniques for building software that's robust and easier to maintain and debug in the long run.
Yeah, whether it's a game engine or any other big project, that AOP approach with a header tool is particularly neat. Automating that kind of boilerplate logging across potentially hundreds of functions saves so much time and ensures consistency.
It's a very powerful pattern for applying those kinds of cross-cutting concerns without tangling up your core logic.
But it does introduce this layer of generated code, right? Code you didn't personally write line by line, which leads to a final thought to maybe chew on. How do you find the right balance? You get huge benefits from auto-generated code, efficiency, consistency, like with this tracing.
Yeah.
But you also need to be able to understand and trust that generated code and potentially debug it if the generation logic itself has a bug or it doesn't do quite what you expected. Where's the sweet spot between the power of generation and the need for direct understanding and control?